time? 10:20. Nice. All right. So that being said here, all right, let me go ahead and read this one here as we get the recording started. All right. So what does it say here? It says, four metal plates, P1, P2, P3, and P4, each have an area of 7.5 square meters. And I think I see conceptually why this could be a challenging one. It's separated by a distance d, and then they give the number here as shown in the figure here. So let me draw that figure that they have, and I think what I'm going to probably point out first, maybe where most people, I don't know about you, but I'm going to say most people probably have a challenge with this one. So the important part here is I'll make reference to the battery. All right, so we've got a 12-volt battery. But then there is this plate, and I'm going to just do a two-dimensional drawing for the moment and see if I need maybe I'll leave a little space. So if I need to adjust it to more of a three-dimension, I will. But here's plate 1, so P1. Here's plate 2. And what's interesting here is that plate 2 is connected to the positive, and plate 1, I'm sorry. Yeah, plate 1, well, that is connected to the negative. But then, this is what's going to make it a little tricky here. There's a switch that allows plate 4 to be also connected to the positive, but only, of course, when the switch is closed. And then there's a plate 3 that is connected with another switch. Yeah, onto plate 3. Now, before I go on and read this, I think I want to do the conceptual. Let me get my colored markers here because I have a feeling this might look better with some color to it. Because what's going to happen first here is there's going to be a positive that builds up on plate 2, but it won't be on both sides. Plate 2 will be pulled over to the left, and a negative charge will build up on plate 1 and get pulled to the right, so that there'll be this field in here. So drawing a electric field in green, that's your standard, what I'd call a single capacitor. Here's where it gets really interesting, and I think this is where the question's going to go, is when you close this switch. No. My other meeting's getting kind of interesting over there. I can tell. I have it muted, so but anyways, so now I can't wait to get to the recording. All right. But watch what happens then when you close these switches. And I'm going to assume, I haven't read it yet, I probably should keep reading, that they're going to close them at the same time, because what will end up happening then is additional positives will build up on plate 2, and then this time on the right-hand side of it, because negatives will go on the left-hand side of plate 3, but also at the same time, negatives will build up on the right-hand side of plate 3, while positives build up on the left-hand side of plate 4. And so there'll be a capacitance between 2 and 3, as well as a capacitance between plates 4 and 3. And so if we called C, the capacitance of one set, then once you close these switches, you really have a series of 3 capacitors in parallel. And so the equivalent capacitance goes to 3C once you close that set of switches. And maybe I'll pause and ask you, do you kind of see that? Do I need to draw that? Like, see how if I was trying to draw the 3 of them, I might do something like this, where I might say, okay, this first capacitor C is really the capacitance between plates 2 and 1. But as soon as I close the switch, more charges come out of the positive battery and go onto the other side of plate 2. So this capacitor is in parallel with the first one in a sense, and its charge is going on this left-hand side of, the right-hand side of plate 2. And so this is between plates 2 and 3. And then also it would be like a third capacitor is here because a positive went on plate 4 and a negative went on the other side. I guess this would be the right-hand side of plate 3. So maybe I'll put plate 3, plate 4 capacitor. This one is plate 2, plate 3 capacitor. And this one is plate 2 and plate 1. And so I think it's kind of hard to see unless you do the first time. So I can understand why you're asking. Kind of realize that when you have a metal plate, there's 2 sides to it. So you could actually kind of use one plate to kind of double up on a capacitor. And that's what we've done with plates 2 and 3. They're kind of doing double duty. Now, 1 and 4 are just kind of doing your regular standard capacitor with charges only on one side. But 2 and 3 are playing a dual role. And so there'll always be a set of capacitors in this configuration, a very common configuration, I should say, that the number of capacitors is 1 less than the number of plates. Because if you have 4 lines, you can have 3 in between. If I had 5 plates, then I'd have 4 in between. And maybe I'll just say that because there is one problem that's a bit of a challenge also. It's number 6. And number 6 has a whole series of plates. I won't try to figure out how many they say. And then I think they just say N. And so the number of capacitors would be N minus 1. Maybe that's a direction in that one. And maybe if you got this far, you didn't say if you've already done number 6, but you've done number 6, you might see, okay, this thinking is the same as number 6. And I don't know, maybe that wasn't the hard part for you. So I'll move on here. We'll now actually then get to the question. So and I'll just start again. It says 4 parallel plates, P1, P2, P3, 4, each have, and they give you the area. They're separated by a distance as shown in the figure. P1 is connected to the negative terminal of the battery. P2 is connected to the positive terminal. The battery maintains a potential difference of 12 volts. If P3 is connected, now, good. And maybe now I should have read it. It sounds like they're not going to close the switches at the same time. Well, I better keep reading. All right. If P3 is connected to the negative terminal, what is the capacitance of the 3-plate system? All right. So in A, they're saying if you just close this switch, they probably should have labeled them. I'm going to put this as switch 2 and this is switch 1. So if all they did was close switch 2, we would not be able to put a positive charge on plate 1. And so that one would be kind of out of the picture. So the equivalent capacitor then would just be plates 1, 2, and 3. And so down here in this drawing, it would be this. It would be a capacitance between P2 and P1 and also P2 and P3. And so this would be twice the capacitance of one of them. And of course, we could even calculate one of them because it's a parallel plate, and the equation for the capacitance of a parallel plate was worked out. That was kind of the first and the easiest one to do. And so it's epsilon naught, and so we call that the permittivity of free space, the area, and the distance between them. So the A, let me just double check that. If P3 is connected to the negative terminal, what is the capacitance? So it would just be 2 of them. So this should be 2 times, and I'll put 8.85 times 10 to the negative 12. And the way they gave me the units, I better be careful here, because this epsilon naught is in the base units. So it's Newton meters squared over coulombs squared. So I really want my area to be in square meters, and they gave it to me in square centimeters. So we've got a little bit of going back to chapter 1 where we got to do a unit conversion. So let's see, they gave me 7.5, and they have centimeters squared. So I'm going to write that instead of as centimeters squared, I'll write it as centa squared meters squared. When I got a spam risk thing coming in. All right, let's get the focus back. Okay, there we go. All right, so there is the area in square meters, which is good because then that will cancel off there. And then D being the distance between the plates, they gave that in millimeters. And so 1.19. And again, instead of millimeters, I'm going to put what milli is equal to. Just like here, centa, I put what it's equal to, 10 to the minus 10. Here I'm going to put milli, and that's 10 to the minus 3, and then meters. And maybe I'll check my units first. That might be a little bit harder than the numbers themselves. But if I look at this, I have down in the bottom a Newton and a meter. Well, that's a joule. And then a joule. Oh, maybe I better come out here. Capacitance is what? Charge over the voltage. Yeah. And so if I take this bottom and call it a joule, but I take one of these coulombs and move it to the denominator, so it's in the bottom here, I'd be left with 1 in the top, so that's coulombs. And then a joule per coulomb is a volt. And so all of this does come out to be a coulomb per volt, which is what we call a farad. So not a surprise, the units work out great. Well, let me grab a calculator then and say, all right, how do the numbers play out here? All right, so we've got a 2 times 8.85 times 10 to the negative 12. Then we got times 7.5 times 10 to the, and I'm just going to put a negative 4. That'll be okay there. That's just squaring that. And then divided by 1.19 times 10 to the negative 3. All right, so 1.1, and I'll round it up to a 2, times 10 to the negative 11 farads. I suppose if you want, you could write that as 11.2, and times 10 to the minus 12. And a minus 12 is a pico. And so 11.2 picofarad would be my answer for A. Since this is the first one here of the day, why don't I look up these solutions before I move on to B? I will see how this one worked out. All right, so, and I probably should have just calculated C by itself because I have a feeling I'm going to need that. But yeah, they got 11.2 picofarads. Nice. Okay, so there's A. We better put page 1 for this, although I don't think this one will go past page 2. You know, hard the next part of this question is, but it might have more than part B, but I think I just, oh yeah, it does. Okay. So yeah, maybe this will go pretty far. So part B says, well, what is the charge on P2? Okay, so since capacitance is charge over voltage, if we come back to our picture here, and at this point, we are not using plate 4. They said just this plate. So I am assuming B is kind of a continuation of A. And so just these two are charged. And so I would have a charge of here and a charge of here. The equivalent capacitance is this. And so P2 has the whole equivalent charge. It has half of it on its left and half of it on its right. So I'm just going to do this. If I want to get the total charge that came out of the battery, which half of it went on to P2 on the left and the other half went on to P2 on the right, I would then take the equivalent capacitance times its voltage. And so this 11.2 picofarads that we just calculated is the equivalent voltage. And we're connected to a 12-volt battery. And I'll just remind myself here that a farad is a coulomb per volt, so that when I multiply by 12 volts will cancel, and I'll be left with coulombs. Probably even just leave it as a pico. So I'll just leave the multiple of the P floating around. And so I will have just the number 11.2 times 12 and get 134.4 picocoulombs of charge, or you wanted to write it as 1.344 times 10 to the, this would be negative 12, and then negative 10 coulombs. And then I'll check that too. They write it as this one right here, 134 pico farads. Good. And then C, what does C say? C says if P4 is now connected to the positive terminal. All right, so coming back to the drawing, they're saying, okay, so now you're going to connect this right here, and that's going to then make a positive charge come on to P4, and at the same time more negative, so you have a third capacitor. So that's this one now added to the mix. In fact, they probably could have put this as switch 1 here, and then this right here as switch 2. So A and B, we had closed switch 2, but not switch 1. And now we are adding P4 to the mix by closing switch 1. So C says if P4 is now connected to the positive terminal, what is the capacitance of it? All right, so as I mentioned, it is 3 times whatever one of them is. So 3 times, and I'll make it easy on myself. If you remember A, we got a total of 11.2, but that's because we had 2 capacitors. So 11.2 divided by 2 would be the capacitance of 1. And so maybe I'll just kind of figure that out. Let's see, 10 and cut in half is 5. So this is 5.6 picofarads is the capacitance of just one of them. All right, so 3 times 5.6. And so that must be 16.8 picofarads for C. And then for D, it says, what is the charge on just plate number 4? Now, again, I'd be a little careful here. If I put the total charge coming out of the battery and put here equivalent capacitance times voltage, that's not what goes on to plate 4. That's the total that comes out of it. And if we look at maybe this picture, we'll see that it goes to plate 2 on the left, goes to plate 2 on the right, and then goes to plate 4. Now, they all have the same voltage and the same capacitance, therefore they're going to have the same charge. So whatever the total is, I can divide it by 3. Not all problems have the same capacitance when they're in parallel, so they don't always have the same charge. But maybe I should emphasize that when I get there. But I'll go ahead and say, all right, the equivalent capacitance is this 16.8 picofarads, and the voltage of all 3 of them hooked in parallel is 12 volts. All right, so if I then take that capacitance and multiply it by 12, I get 201.6 pico. And again, a farad coming back to here is a coulomb per volt. Volt comes up, and we just get coulombs. Now, that again is the total. Let me point out then that maybe the capacitance of number 1 is charge on number 1 divided by this 12 volts. Capacitance of number 2 would be charge number 2 divided by the 12 volts. And capacitance number 3 would be charge on number 3 over the voltage. And that's really what we want. We really want the charge on number 3. Get back to the picture. Number 3 is the charge on plate 4, and that's what they're asking. What is the charge on plate number 4? And so I've called this capacitor 1, 2, and 3, but I maybe am doing it the long way, in the sense that I wanted you to see mathematically that if they have the same voltage, so they're in parallel, if they had different capacitance, they would also have different charges. So I'm not saying that they always have the same charge, but for this problem, they have the same capacitance. So this C1 and C2 and C3 are all the same, which means Q1, Q2, and Q3 are all the same. And this number here is that total of Q1 plus Q2 plus Q3. That is the charge that comes out of the battery and goes on to, like I said, the left-hand side of plate 2, the right-hand side of plate 2, and the left-hand side of plate 4. And so everything here, so kind of an easier problem that it could have been, is that they all have the same size to them. So that means if I take this total of 201.6 and divide it by 3, I will get the charge that's on number 4. And for that matter, it would be the charge that is on the left-hand side of plate 2 and on the right-hand side of plate 2. So I guess I'd have to double it for how much is on plate 2. But that hadn't changed. That was still what we did back there. So I guess technically we could have even just cut that in half. But if I take that 201.6 and divide it by 3, I get my 67.2, And just to confirm, if I were to double it, I should get what we said was on plate 2, because that would be that much on each side. So plate 2 had that twice. And yay, I think that was the end. Maybe I'll check the answer here. Let's see. I already checked B. C, I didn't check. 16 points. Well, they got 7, so a little rounding there. And then a little rounding here because I got 66.9, but nice. Oh, and I see how they. What is that drawing? Oh, my bad. That drawing is for the next problem. I was like, wait, looking drawing. Okay, good. And then, thanks. All right, that helped, Johnny.
Yeah, thank you so much. It was I don't know, it was kind of hard to picture the circuit, but once you explain that,
yeah,
rest are pretty straightforward. Thank you.
Okay, good. Yep. Yeah, it is hard to see that. All right. Yeah, Sasha came in here, but let's see, anybody else? Let me jump back to the Zoom chat here. All right. Well, I don't have anything more in the chat, but it looks like it's just the two of you at the moment. And so if you got anything for me, either way, put it in the chat or orally, that's fine.
Yeah, sure. Let's see. Maybe problem 6.
Okay. And number 6, and I'm going to assume this is chapter 26.
Or actually, sorry. Maybe another one, because
Okay.
I know that you have a video on it anyways. So I haven't looked at it.
Oh, okay, good. I'm glad you remember.
Yeah. I have like a little V under the ones where you have the video.
Good.
Yeah. Maybe 52 then.
Okay. So, all right, so I'll try number 52, and it looks like the time is 10:47. And so I'll just put here to help people scan the video better here. Chapter 26, number 52. All right, I get it. All right, so let me switch over. Actually, you know what I'm going to do? Let me rearrange my tabs here. And put all my other stuff over here, tabs like email, stuff I need to do at the break. All right, and then get you guys is in one organized side of my screen. All right, so 52 is 2 down. It says this. It says a horizontal parallel plate with a vacuum between its plates has a capacitance of 25 microfarads. All right, so maybe for starters, I'm just going to draw a set of metal plates kind of horizontally. Maybe I'll put some leads on here. Maybe I'll put a C and just say, okay, so 25 microfarads for starters. All right, so horizontal parallel plate with a vacuum between them has a capacitance of 25 microfarads. A non-conducting liquid. I'm glad they say non-conducting, but I hope it's also implied. I'll just say a little bit about the physics of it, that obviously if you put something between them that conduct, you would not have a capacitor anymore. It would now conduct through. So the stuff that goes in between has to be a non-conductor, and we call that a dielectric. So here, a non-conducting liquid with a dielectric constant of, and so I'm going to just kind of put maybe kind of a blue color. So we kind of fill this up with a liquid. Oh, and it's a fraction. Okay, I'm going to redraw my picture here. But for starters, I'm going to say if I filled this all the way up with a dielectric constant, and the symbol for the dielectric constant is the Greek letter kappa. And forgive me, I'm not real good at making kappas. In fact, the only person I've ever come across who's really good with their kappas was a native Greek faculty member. So that, I guess, maybe explains why they're so good with their Greek letters. But I say that because a lot of people will call that K, and I think that's not good. It kind of indicates that kind of like in mechanics in 121 omega, again, our omegas tend to look like W's for us non-Greek people, but you start calling it W. My little warning for you students is it comes across as you don't really know what's going on. Like, wait a minute. The angular speed is not measured in W. The angular speed is measured with omega. In fact, all the angular stuff is the Greek. Anyways, and so here in our electronics, things like the prefixes and, well, not all the prefixes, some of the prefixes anyways, and some of those anyway. So let me be sure to refer to it as a kappa and just point that out. But here's what I need to say before I read the rest of the problem here then is that the capacitance for a parallel plate capacitor was derived to be this much. And the epsilon naught was called the permittivity of free space. And of course, that capacitance built up because if you don't put anything between them, the electric field is created in free space. But as we got later in the chapter, when we started putting things other than free space between them, it had an effect on us. And so for the first time this semester, we've actually been talking about, well, what if our electric field is not in free space? Now, I must say most of our fields, both electric and magnetic for this class, are really more free, what we call free space fields, because it's a step harder when you start putting material in them. And so that's better to wait for the next semester. There's a few exceptions where we introduce it, and I would say this is that time. And so if I put a little kappa here, the capacitance goes up by the same amount that it weakened the field, and that's what kappa represents. Kappa is a number by saying, okay, if you take a field that's in free space and then you put that field, or you put something where that free space is, and you no longer have free space, you have something different. And so this together is the permittivity of that material. It is the free space, and then how much has it been affected by that material, what multiplication factor. So in our case, it's a pretty good sized number. It's 6.5. And so the electric field has been reduced by 6.5, also meaning the capacitance has gone up by 6.5. Okay, so that's a little background on capacitors and their dielectric here. But this is saying here that a non-conducting liquid with dielectric constant of 6.5 is poured into the space between the plates, filling in a fraction F of its volume. Now I see why they said this was horizontal. So I'm gonna redraw this. So here is the top plate, the electrode going up. Let me give my space a little more space here. Here's the bottom one. Maybe even on the sides, I'll put what would be the container boundaries. Okay, and so when you start filling up the liquid, and for starters, why don't I just draw a line right here? Okay, and so obviously below that is filled with this liquid. And the only part that in terms of electronics that are relevant are going to be right here. I'm not going to worry about the liquid over here. But if I was looking then at the electric field, what would happen course, depending on how you charge this, I'll just make the top plate positive. So there'll be a bunch of positives up here. And that would make a field now, when it hits this material right here, the field's going to be reduced some. In fact, it's going to be reduced by a factor of 6.5. So it gets reduced because this liquid, whatever it is, says non-conducting. I don't want to call it water, although surprisingly, water is not really a good conductor in pure water. Problem is we never really have pure water. We always have ions and so many things dissolve. But without me calling it any kind of liquid, let me draw kind of a molecule that might be in here. And if it was water, the oxygen atom would grab the electrons and pull them away from the hydrogen. The whole molecule would be neutral, but one side would be more negative than the other. And so we like to say water is a polar molecule. And so whatever this material is, it too is going to have this polarizing effect. And here's why that's relevant. I still didn't really give myself a lot of room to draw this, but what will happen then, because of the positive charges up here, is the water molecules up here on this surface will have their negative ends tilted. So like the molecule was just kind of floating around and this was the negative end, it would pull it up. And so I would get the molecules on the surface to be kind of in a vertical position of the way I've drawn them anyways. And so if you kind of think of this as an ellipse, how about a hot dog? A hot dog phase molecule, it gets twisted around and you get a bunch of negatives on the surface. That's essentially why the electric field has been reduced. And if the number of negatives from the molecules was equal to the number of positives, it would actually stop. It would actually terminate the electric field, but it doesn't do that. It tells us it reduces it by a factor of 6.5. Okay. So 6.5 is a good reduction, but it's not the whole thing. And so that, let me just call it 6 for a moment. So if I have 6 lines coming down, 5 of them get terminated and 1 continues on. So I'll just draw 1 here and 1 here and maybe just a third one here. So I'm trying to draw in my picture so you can kind of have a conceptual feel here that this field has now been reduced by a lot because of the charges that are in the material. That's, again, why we have an effect on the electric field. So that's why we have the permittivity of free space versus this dielectric constant, which we call these two together, the permeability of this dielectric, whatever it is, this liquid. Okay, so what ends up happening then is you get something like this on the bottom plate. Now, I'll draw some more molecules here. And so this second row of molecules would line up the same way, because remember this bottom of this top one is plus, so maybe I have a little more room to draw. I'll draw it down here. But the negatives of this second row and the positives down here means that right along this bottom edge, I have a bunch of positives. And the number of positives on that bottom edge is actually the same as the negative on the top edge of the water, which is now perfect because remember, then there's going to be a bunch of negatives on this plate down here. And the number of negatives on this bottom plate is actually the same as the number of positives on this positive plate, which you might say right here, just microscopically above where these positives are, the field gets heavier again. It gets back to this normal value, which then terminates with the equal number of negatives down here with that positive. So the field has been affected in this area. So what am I trying to say in all this is you can view this, and this is the key to the problem. I better put page 1 here because I think this is going to go a little bit. Page 2. What I'm trying to say then is something like this. You can view it as capacitor number 1 here. Okay. Then in series with it, capacitor number 2. And so I have, instead of a 25 microfarad capacitor, that's what I would get if I had only air. Now I get 2 capacitors, okay? And let me just say the total distance between the 2 plates is D. Now, maybe before I get too far in all the other neat little things that can happen here, I better focus my attention on what are they asking. So let me come back to the reading here. So it says a horizontal parallel plate with a vacuum between the plates has a capacitance of 25. So that's the first thing. Then a non-conductive liquid with a dielectric constant of 6.5 is then poured into the space between the plates, filling up by a fraction F of its volume. So back here, I might say that this spacing is F over D, and this spacing here would be 1 minus F times D. For example, let's say the fraction was 40%. So the distance of the liquid is 40% of D, whereas the distance of the non-liquid, that is free space, would be 1 minus 40. So that'd be 60% D. I'll give another example. Let's say we filled it up 30%. Okay, so this down here would be a distance of 30%, and this up here would be a distance of 70%. So this is the math that they're saying here, that if the whole distance between them is D, then I have FD for the part that has the liquid, and I have 1 minus F times D for the part that is still free space. So keep that math in mind. So the spacing for capacitor number 2 is FD. The spacing for capacitor 1 is 1 minus FD. And so that would be our 2 capacitors in series. And that's how we're going to look at it. See, so here is what A says. Find the new capacitance as a function of F. All right, so the big piece of this puzzle I wanted you to get, and maybe I spent too much time talking about the conceptual nature of how this is an electric field and reduced, and therefore it's really like there's two capacitors in here. But I'm hoping that description explains why I'm going to treat them now as two capacitors in series. And that's maybe the biggest step of this problem, is to realize, okay, how are you going to treat this? And you can treat this as the equivalent of two capacitors in series. And the chapter did a lot with capacitors in series and in parallel. So I'm going to use those skills to answer this problem. For, in other words, the 1 over the equivalence capacitance is 1 over C1 plus 1 over C2. And so that's how we treat capacitors that are in series. We can get their equivalent. So let me go separately here. Let's talk about capacitance number 1. Okay, capacitance number 1 would be a free space capacitance. So it would be epsilon naught, okay, times the area of this top plate. I didn't really draw kind of 3 dimensions, but there would be an area to this top plate. It would be the same as this bottom plate, and the same as the top plate of number 2, and the same as the bottom plate. Because again, back to this picture, this capacitor here and fills with a liquid, and so it's the same area here. So this capacitor number 1 has some area. And then we separate it by its distance. Well, its distance is 1 minus FD. That was my mathematics on percentages. If this is F field, then what's remaining is 1 minus F. Now, maybe again, I'll just do another number, say 90%. So if this is 90% filled of liquid, then 10% remains above. Okay, so that would be capacitor number 1. Let me do the same logic with capacitor number 2. Now, capacitor number 2 is this one that's the liquid. So it would be the kappa dielectric constant times the permeability of free space times the area divided by the distance separating the two plates. And so capacitor number 2 is separated by FD. So if I take that and put it into here, 1 over the equivalence, and that's what we want to find, the equivalence, and I'll read the question again here. It says, find the new capacitance. So we're really saying, now that we filled it with a fraction, what is that equivalent to? So, all right, so I'm going to put this in. And so this says, take the reciprocal of C1. So if you don't mind, I'll just do that right at the beginning here. Okay, so that's the reciprocal of C1, and then add it to the reciprocal of C2. So this would be FD over kappa epsilon A. Now, well, I'll keep going. I was going to say, let's talk about the meaning of these, but maybe I'll just do the math and get a common denominator here. So this is kappa epsilon A for a common denominator. So this would be kappa 1 minus F times D plus FD. And that's the equivalent capacitor. Or maybe I'll flip. Well, no, before I flip it, let me do this. Let me factor out a D here. So I'm going to factor out a D. I'm also going to group it with the epsilon naught and the area. That means downstairs I'm left with a kappa. And over here I have a kappa 1 minus D, kappa 1 minus D, factored out a D, plus oh, sorry, not 1 minus D, 1 minus F. Kappa 1 minus F, and I factored out the D, plus an F. Now, here's why I wanted to do that, because if I take the reciprocal now, yeah, I have kappa on top, and this right here would be this kappa 1 minus F plus F. But it's this right here, when I flip it upside down and group it together, makes me realize that, wait a minute, this is the meaning of the 25 microfarad to begin with, right? When they told me the capacitance has 25 microfarads, they were saying, well, in free space. So this calculation right here is the 25 microfarad. So I could use that to my advantage right here and then put in my other numbers. When I say my other numbers, I mean the kappa. So this would be 6.5. This would be 6.51 minus F plus F. And this right here would be 25 microfarads. Maybe I got a little more room on this page here. But let me see what this gets me. Maybe I'll multiply those together. So 25 times 6.5 would be 162.5 microfarads. This right here would be 6.5. And then it would be minus, yeah. So it looks like this would be 6.5 F and then plus an F, leaving me with 5.5 fraction. And so there I have an equation for the equivalent capacitance that is based upon this factor of F. Now, maybe before I continue too far, maybe I should scan the solutions and see what they got. Okay. I think we got the same thing. They do write it a little different. Let me just verify that. It looks like what they did is they left the 25 microfarads alone. And they actually took the 6.5 and brought it underneath here. So that what you would get is this canceling, and you get a 1 minus an F plus, and then on this side would be 1 divided by 6.5. And so 0.154 F. And then simplifying that, they get 25 microfarads over. And so if I take a -1 and add the last answer, I get 1 minus 0.848 F. And that's, let me see what they got. Yeah. And so that's how they got. And that's how they write it. Actually, they do one more. They move this up into the numerator. So they have 25 microfarads, 1 minus 0.848 F to the -1 power. Not sure I like it written that way. But I do like this. This is actually a neat way to write it. And it's the same thing here if I were to, divide top and bottom by 6.5. If I divided the top by 6.5, I would get 25. And the bottom, this 6.5 would become a 1 over here. And then this 5.5 over 6.5 would become 0.848. So these are definitely the same. And this is even the same. But like I said, writing it with a negative exponent is not my first choice, but that's the way they wrote it. All right. So we agree here with the answer from the book, but I think they also told us, I remember reading this one earlier this week. Somebody didn't understand the question, so I had to kind of explain the question to them. They kind of help you out, and this is kind of a good common strategy. When you get something that you wonder, does this even make sense? Is this even right? Sometimes it's good to check. And what I mean by that is, let's say that you had zero fluid in. So if F equaled 0, I would expect to get back what they started with, which is 25 microfarads. Okay, so let's put that in here. So if I take 162.5 and I put in F equal to 0, I would get 6.5, which is 25. Okay, so that seems to work. What about the other extreme? What about if F equaled 1, 100%? We fill this whole thing up. So again, coming back to this discussion, that if you filled the whole thing up with a dielectric, you would have this number, which is 25 multiplied by 6.5. And so 25 times 6.5 is 162.5. And so if you filled it all the way up, in other words, if F equals 1, I would expect this little equation to come out to be 162. And what does it come out to be? Well, let's see. If I put 1 there, that would be 6.5 minus 5.5. That's 1 divided by, and 1 divided by, or something divided by 1 is just stays the same. So this is 162. So that's kind of what they're thinking. They're thinking, look, you got a weird looking formula. You kind of want to know if you did it right or made a mistake. Try some things that you know. And so in this case, we know completely empty and completely filled. So try F equals 0 and F equals 1. And so that's what they're asking here. It says in, where does it say here? Does your part, what it comes in? A says, find the new capacitance as a function of F. B, what should you expect the capacitance to be when F is equal to 0? Well, I expect it to be 25. And yes, it does match. What capacitance would you expect if it was 1? So I guess technically this is question C. I would expect it to be 162.5. Okay. So they seem to check out, and that's what they're answering. It says, does your answer in part A agree with your F equal 1? Mm-hmm. Now D, looks like D might be a little harder. Charges of magnitude 300 microfarads are placed on the plates that are partially filled capacitor. What can you determine about the induced charge on the free upper surface of the liquid? And how does this charge depend on F? Yeah, now that one's I think a little trickier. Let's see. How should I do this? We look at the charge on the lower plate and the upper plate. Okay, so yeah. All right, so I guess I'm gonna do this. The electric field in free space was this sigma over A. Okay. So for the top plate, this would be Q, which they gave as 300 microfarads. So I'll leave that alone. And then, oh, I'm sorry. It's sigma over epsilon naught. And sigma is Q over A with the epsilon naught. That's what it looks like. Something wasn't sitting right. Okay, so this is the 300, and this is the area of the plate. Okay, now for the bottom plate, the field gets reduced. So field at the top reduced by kappa. And so that was the fundamental idea of what is the dielectric constant? What is it doing? Oops, I didn't mean to put total, I meant to put top. So this would be what we just did at the top. So I'll put the charge at the top, and then a kappa and an epsilon naught and an A. Okay. Now, here's where I'm kind of glad I maybe spent the time talking about this. If I say this right, remember when I was drawing these fields, I said there would be a little negative charges that built up on this surface, and that's what they call the induced charge. And that's really what this question is asking. You know, what is that induced charge? Okay. And I think just understanding the physics of why there is an induced charge is a bit of a challenge. So again, now I'm glad at the beginning I went through kind of a long-winded explanation of, okay, what's going on here? There are these induced charges here. But maybe at the bottom, you can kind of see here that if you, I guess I want to say this, that the field in the bottom, now I want to say it this way, the field in the bottom plus, I'll call it the amount that's stopped or reduced, has to equal the field at the top. So come back to my little description here. So I've got this field that's generated at the top, which we just said was the charge over epsilon naught A. Okay. Then that field gets stopped. Okay. And so I would say it gets stopped by this induced charge. So let me call this sigma induced over epsilon naught. And that's that little surface charge. And then, as I was trying to say, it wouldn't stop all of them. That's why I drew, and it's gotten kind of busy in here now, but I originally drew 1, 2, and 3 electrical field lines going through. So this charge is not enough to equal that one. It doesn't stop the whole field. There still is some field left over. And that's what this bottom one is. So this would be Q kappa epsilon naught A. And in fact, let me take one more step here. And now I think we got it. This induced charge up here or I should say induced sigma, would be the charge that is induced divided by that area. And then let me not forget the epsilon naught. So I guess what I'm trying to do is trying to say here is this meaning of the field and how much stop fit is this induced charge. And that's what I'm trying to do then. And so find out the equivalent of this induced charge. So I'm using the real charges, if you will. So these are the real charges. And then this is what is induced. So fortunately, there is the permeability of free space, and there is also the area on each one. So I'm not even going to need those. And so what I'll call this induced charge then would be the complete charge minus the charge divided by kappa. And again, that's a terrible looking kappa. Or maybe factoring out the real charge, I would have 1 minus 1 over kappa. So this would be 300 microcoulombs, 1 minus 1 over 6.5. And so grabbing a calculator, 1 minus the reciprocal of 6.5 is, that same fraction. That makes sense. And then times 300 would be 253 micro. And so we stopped a lot of it. In fact, don't be surprised if 253 divided by the original 300 is, of course, that same fraction, that 1 over kappa, because that's what the kappa means all the way through this problem, how much the field has been reduced. And it's been reduced because you might say how much charge was induced. The reciprocal of that would be how much would be induced on the surface. That's what's stopping it. Okay. So D, I think, is a little bit tough here. Let me switch over to the solution and see what your author does here. Does your author do? Oh, okay. So he essentially does the same thing, and he comes up with 254. Okay, so other than some rounding. Good. I forgot that the problem said something about does it depend on the fraction, and no, it doesn't depend upon the fraction field. I should have said conceptually that made sense, because regardless of how much it filled, we have to reduce the field by that same percentage. So as we fill this liquid up here, we're going to reduce our field into the story. And so we reduce it by that same factor. It's just a matter of what spacing is done before it gets reduced. So the amount of charge building up on this liquid surface, this induced charge from the negatives of the polar molecules that are sticking I'll call it their rear end up in the fluid. It's the same number regardless of what F is. And then your author says the sign. So I guess I should be careful. So up here in the fluid, that is close. This would be a negative if the top part was positive, or maybe I should just say it's opposite of that plate. I don't remember them telling me what the top plate was, so I'm not sure I can say the top surface was negative. I just know it's opposite. What does the author say? The induced charge will be opposite of the sign of the charge on the top plate, and the same sign as the charge on the lower plate. Yeah, so in my case, I put negatives here. So negative on the lower plate and negative of the induced charge if the capacitor had been hooked up the other way, so that this up here was negative, the induced charge would be positive, which would be the same as the bottom plate. Yeah, so the best we can say is the charge would be the same as the bottom plate. Yeah, that was a hard one. Let's see. Charges of magnitude 2 are then placed on the plate, partially filled. What can you determine about the induced charge on the upper end of the liquid, and how does it change with F? Yeah, it does not change with F. it's 253 micro coulombs. And that's what it is, regardless of what F is. And it's the same as the bottom plate. Nice. That was good.
Question.
Yeah.
So would the direction of east stop mean anything? Like, would it be opposite maybe to the direction of the electric field from the top?
Oh, no, it wouldn't be opposite. And let me also say something else. I guess what I really meant is that, these magnitudes were the same because they are in the same direction. So I guess if I kind of draw this picture, I'm kind of saying, okay, so I've got this electric field. Let's say it's a real powerful electric field. So I'll draw it every line. And of course, it would have started here with a plus. And I say stop, and I suppose maybe a better word was reduce, because if you have something in this area right here to kind of reduce the field, so in other words, the field on the other side is just a few lines. To terminate them means you have to have some negatives here. So in my kind of picture here, I've got 1, 2, 3, 4, 5, 6 lines, and only 2 continue on. So I have to have 4 charges. Each of these negative ones terminate them. And so what I'm really should have said, I shouldn't really have said field. I should say